Welcome to the Innovation Fair 2012, Caltrans District 4, Division of Right-of-Way, Office of Field Surveys. Today I would like to talk about our new technologies. We'd like to start out with ground penetrating radar, GPR. And for the example I'm going to speak of is for the SFOBB complex here in Alameda. It's a 12-acre site. And the scope of work was to use a three-dimensional device to depict underground facilities and structures. What we used was a ground penetrating radar, SIR 3000. The field data was processing using the GSSI radon software. The area of 12.5 acres was broken into 18 grids. We break these grids into the area into smaller grids so it's workable for the devices we're using. The size and shape of each grid is based on a maximum grid size and minimal physical obstructions. A coordinate system with origin at the southwest of each grid was laid out on the ground. Each corner was identified by a unique number and a marked PK nail. Our spacing for this particular project was 2 feet. So every 2 feet we took a ground sample to find any underground obstructions. This slide is showing the GPR grid layout. As you'll notice, there's 18 perfect squares in there. Each corner of the square was coordinated with geospatial values placed by Caltrans surveyors. And on this slide, we show the GPR unit itself. On the left is the cart, which they push in the field, and it takes the samplings. On the right is the display or operator display. And on this slide, I'm showing how many samples were taken in this 192 foot by 146 foot grid. And in this slide, I'm showing what the operator would see in the field. The red arrow is pointing to a pipe, underground pipe, and the arrow on the right is pointing to a structural foundation. And please note that most of the underground facilities here are not disclosed of record. This is a perfect tool for that scenario. If you don't know where the utilities are, but you have a hunch that they're there, this is the tool to use. And on this slide, you'll notice we have placed together all of the site's readings. The white or bright pixelization is where facilities are located. On this slide, we just show one complete grid in 3D. On this slide, I've placed all the grids together into AutoCAD or preparing it for casing. This slide shows it after the data is in casing and a cross-section, random cross-section was taken, and you can see that the underground facilities do show up underneath the DTM. This slide shows an aerial photo with all the line work imposed. The line work of the underground is in red and blue. Conclusions. Ground penetrating radar was an effective tool to designate the location of underground utilities. GPR 3D modeling was able to provide the X, Y, and Z location of each pipe at any point within each grid. GPR does not provide information on the type of underground facility. GPS data collected at 2 opposite corners of each scanned grid facilitated the position of each grid within the surveyed area. Additional information on possible buried targets other than underground utilities was shown on each GPR 3D model. In other words, whatever they find, we're going to show it. They may come up as unknown, but you'll know the facility is there. I would like to move on to multi-beam sonar. This slide shows an area of scour on the Russian River for the Geyserville Bridge. The scope of work was a 3D topography of the surface below the water, approximately 700 feet upstream and downstream from the bridge. Detail of the geotechnical system recently constructed to prevent scouring. Provide data as XYZI ASCII2 format. Geodetic control provided by Caltrans. In areas of shallow water, conventional survey techniques were used. The sonar was performed using a radio-controlled vessel, RCSV, an echo sounder, altimeter, to determine the depth. Operating range of this device is anywhere from 0.1 to 10 meters, making it ideal for shallow water applications. Extensive overlap of the data was achieved between the data from the RCSV and that from the conventional survey techniques for quality checks and redundancy. This slide shows the area of interest as a heat map. And what it is, it's classified by elevation, reds being high, blues being low. This is a really good visual aid for the geotechnical engineers to see if their system is actually working. This photo is the RCSV being controlled by an operator who's safely on the bank. And in the foreground, you can see the instrument, which is a conventional survey instrument, robotic, which is tracking the remote control vessel. And in this picture, on the left, is collection of data points in real time. So the operator can see actually what he's gaining, if he's getting overlap, and where the overlap should take. And on the right, the collected data in the processing software. And in this photo, the bathymetry is fused with static LiDAR of the Russian River. In this view, I'm showing the mobile LiDAR, and right now it is a dual head system that's collecting about 400,000 points per second. And on the right is one of our static LiDARs. It's the C10 that collects approximately 50,000 points per second. In this slide, I'm demonstrating the use of data mines. In this particular case, we had existing mobile LiDAR on Interstate 880 in Alameda. However, a year later, another project had arisen, so we were able to utilize the data mined. And in this case, what we were interested in is the clearance of an overhead structure, which these routines are becoming automated, where we just define the structure, the roadway surface, and then we'll get clearances either horizontally or vertically. And in this case is a data mine from static scanning. On the left is a point cloud of a architectural wall in the Presidio. And the point of this was to reconstruct this wall in its exact location where it originally was placed. So into the data mine, I was able to coordinate the location of the wall and the details of the wall, which is the picture on the right. The picture on the right was given to the contractor to reconstruct the wall in its original location. And in this photo, we've taken design information and we've fused it to the cloud. On the left is the point cloud itself, and on the right is where we've taken design information, 3D information, and put it into the 3D point cloud. And this would be for visual purposes to ensure that the design is meeting the standards that were set forth. And in conclusion, these remote sensing technologies are effective tools to add project value. It is design-grade data. It has a quick turnaround from field to finished deliverable. It is seamless information, geospatially correct, great use for data mining. It's great for the safety for the traveling public, for we don't have surveyors on the ground. Safety for Caltrans employees, consultants, and contractors. It is visual and fits right into the VDC and BIM environments. It's perfect for animations, public outreach, and analytical analysis. We encourage the client to tour our models to find information not previously requested or that they may not know exists. Thank you, and have a good day.